Now let's take a look at a couple of theorems that deal with integrable functions, shall we? So this theorem says that if f and g, which of course those are functions, I don't write that every time, we just assume they are. If f and g are functions that are integrable on the closed interval a to b, and if f of x is greater than or equal to g of x for every single x in that closed interval, then what we can guarantee is that the definite integral from a to b of f of x with respect to x is also going to be greater than or equal to the definite integral from a to b of g of x with respect to x. So that just seems to make sense. That's a nice follow there. So basically we know that f and g are integrable on the closed interval, and f is bigger than or equal to g the whole time, then the definite integral of f is going to be bigger than or equal to the definite integral of g. So I drew up a couple of examples with this. In the first case, I've got f and g both being positive or above the x-axis in quadrant 1 here from a to b. But if you notice, the definite integral of f of x with respect to x is actually indicated by the red shaded part, which in this case actually equals the area under the curve. So if you remember that application. And then of course the area under the g curve, of course I used red for f for fuchsia, and I used g for green. Pretty inventive, right? And then for the definite integral from a to b of g of x, since g of x is entirely on or above the x-axis here, this actually represents the area under the curve as well of that plane region between the x-axis and g of x, and the lines x equals a and x equals b. But notice that the red area is going to be bigger than, in this case strictly bigger than, the green area. So we've got some distance in between here, but of course we can always put an equal sign in case it happens to be the exact same curve, then it would be the exact same equality here too. But since f is strictly above g of x in this case, the area is going to be strictly greater than the area of underneath g of x. So let's look at another one. So what happens if they're below the x-axis? Well, in this case, for f of x to be greater than or equal to g of x, it has to lie above it, correct? So closer to the x-axis in this case. And if you remember, so the definite integral from a to b of f of x is going to be a negative number that actually, if you took the opposite of it, would represent the area of the red section. And the definite integral from a to b of g of x with respect to x is a negative number as well, but it's more negative. So once again, we'd have to take the opposite of that to have it be the true area of that curve between the x-axis and that function g of x. So in this case, the definite integral from a to b of f of x is greater than the definite integral from a to b of g of x with respect to x because it's less negative. So now I know you see another picture over here. Don't worry on that one. That's for a different theorem. So we're going to save that one. But let's look at one more theorem. And let's just look at a single function f. And so in this case, what we're going to say is if f is continuous. So once again, if that's different than what we had, we just said f and g were integrable. But if f is continuous on the closed interval a to b, that means you can draw the graph without lifting your pen, that it has no holes, rips, tears, jumps, etc. And if the absolute max, we're going to let little m be the absolute minimum, and the absolute maximum we're going to call capital M. So we do know that the function is going to be bigger than or equal to its absolute minimum and less than or equal to its absolute maximum. So we know if f is continuous on this closed interval that it will have at least one height value that yields that's its absolute max, and it's going to at least one x value that maps to the absolute max, and it's going to have at least one absolute minimum x value that gets mapped to the minimum height value, little m. So I don't know if you can tell the difference between my little m and my big M, but this is the absolute minimum height right here. Once again, these are heights. This is the absolute max height. Here we know that this function will have an absolute maximum and an absolute minimum height because it's continuous. That was a previous theorem that we had. What else do we know? We also now know that if f is continuous on the closed interval, then by a previous video that we had a theorem that said f is integrable from a to b. So the definite integral is going to exist from a to b as well. So we could actually prove this. What we know, since I did draw this entirely on or above the x-axis, we know that right here yields our absolute maximum height on that closed interval. We also come up with critical numbers, right? So it's where the derivative is 0 or undefined, as well as the endpoints would yield potential absolute extrema, right? So then we've got our absolute minimum height right here. But since we're entirely on or above the x-axis here, the reality is what this definite integral would be here from a to b of f of x with respect to x would actually be the area of this plane region between f of x, the x-axis, and the lines x equals a and x equals b. So the area is actually equal to that definite integral the way I drew my picture here for this f of x. So once again, if f of x was all the way underneath or part of it was underneath the x-axis, that's not the case. But in this case, the way I drew it, that's going to be the case. So we're going to use that as our concept here. And so what we know is if f is continuous and the absolute minimum is less than or equal to f of x, which is less than or equal to absolute maximum, which is always going to be the case here, then what we're going to have is that m times little m times b minus a is going to be less than or equal to the definite integral from a to b of f of x with respect to x, which is going to be less than or equal to the absolute max times b minus a. So this is the conclusion here for our theorem. So if f is continuous and little m is less than or equal to f of x is less than or equal to capital M, then little m times b minus a is less than or equal to this definite integral, which is less than or equal to capital M times b minus a. And what I'd like to do is I'd like to prove this, and we're going to prove this in parts. So the first thing we're going to do is we're going to prove the left part. And since the one above the x-axis with the less area was green, I'm gonna look at this one in green. So in this case, we know that capital F of x is greater than or equal to little m on, that's one extra hump there, on the closed interval a to b, right? So we do already know this. So then what we can say then is that the definite integral from a to b of f of x with respect to x is going to be greater than or equal to the definite integral from a to b of little m with respect to x. So this is the theorem that we had up here first. And so we know that. First of all, we said the theorem that we had up there before said if f was integrable, and in this case g of x is m equal to m if those are integrable. Well, a constant function is going to be integrable, and we know that if a function is continuous, then it's going to be integrable, so it satisfies that previous theorem. So we do know this. This is going to be the case here. And then what we can actually do is use a derivative theorem here that says the definite integral from a to b of a constant, remember that's a constant height, or that's a height, which is just a number with respect to x, is going to actually equal the constant, which in this case is little m, times b minus a. So that was a theorem that I gave you in a previous video, right? So we do know that the definite integral from a to b of f of x with respect to x is going to be greater than or equal to little m times b minus a. Now let's look at that. What would that look like over here? Here's little m. And so there's my height equaling to a constant height of little m. And if I look at this green under here, that's little m times b minus a. So basically base times height would be b minus a times little m, right? And obviously the black area is going to be bigger than or equal to the green area there. So we do have this left side there, and then we could also show the right side here. So once again, we'll finish this up here. And so now I've got, what do I know? I know that m is capital M, so that's the absolute max height, is greater than or equal to f of x on the closed interval a to b, right? So the absolute max is bigger than or equal to the function for every x in that interval. And so then by using our theorem that we had on the board earlier, so that implies the definite integral from a to b of capital M with respect to x is going to be greater than or equal to the definite integral from a to b of f of x with respect to x, right? So you see where this is going, very similar to what we did before. This is the antiderivative from a to b of a constant. So basically, that's going to be that constant, capital M, times b minus a. Once again, a visual interpretation of this is basically we just made a box now, and I'll try and go in the opposite direction with the red here. So the area of the red box is capital M, which is the height, times the base, b minus a, right? So obviously that area has area that the function didn't have. So we got area up here, right in there, and we've got area in here that we didn't have for the black area underneath that curve. So anyway, this is going to be greater than or equal to the definite integral from a to b of f of x with respect to x by our previous theorem. And that's what we had here. Notice what we have. The definite integral from a to b of f of x with respect to x is greater than or equal to little m times b minus a. And it's less than or equal to capital M times b minus a. So this is a nice proof that utilizes the previous theorem, which really this would be a corollary to that previous theorem, or you could say that previous theorem is a lemma to this theorem here. So a couple of nice theorems, nice results that talk about the definite integral from a to b of a function.